Okay, hello everyone. So today we'll continue from yesterday about Math3311, or the postgrad version of this course. So yesterday, Ehhrm kind of went through topic 1 to 6, and today I will be going through topic 7 to 11, which mainly cover questions 3 and 4 in the final exam. If you tried past paper, you should realize that the last question will always be about Black-Scholes, right? So something about topic 10 and topic 11. So obviously, it's quite important. So today we'll cover more trading and quant finance related knowledge. So hopefully it's gonna be fun. So we'll have 5 topics. We'll start with Black-Scholes model, implied volatility and nonlinear equations. So we'll talk through some numerical method to kind of estimate implied volatility. We'll do numerical integration, as in how we can approximate integration over a given interval. We'll do random numbers and simulations, so mainly the Monte Carlo and quasi-Monte Carlo simulation methods. And then we'll go to stochastic differential equations as well as a finite difference method for the partial differential equations. So let's start with implied volatility and nonlinear equation. So maybe I can briefly kind of introduce the financial intuition behind a pull and a call. So maybe I'll just add a new page. So I just want to highlight that, I guess it's also on my slide, that underlying asset can be anything such as equity or stock price or even government bond. It has nothing to do with call or put option. So options are what we call financial instruments. They are used to trade the underlying asset. And the reason why we want options, so there are a few reasons we need options, but one of the reasons is to hedge market risk, or to kind of provide some financial protection on our underlying asset when the market become very volatile. So let's just suppose that our underlying asset is gold in this example. So basically, we'll only focus on European options, I guess, in this course. So option just means you have the obligation, you do not have the obligation, but you have the choice to buy or sell your financial product, I guess, at a certain maturity time t. So let's assume that now we are at time 0. And our maturity time is capital T. And maybe let's assume it's 2 months in our example. Sorry, just let me change my color very quickly. Right, so now we are standing at time T, and our maturity time is 2 months later. I think in all the tutorial question, we assume T is in days, right? So our risk-free rate is the daily risk-free rate. Our implied volatility is the daily volatility. But T can really be in any time unit, so just be extra careful in the final exam. And let's see, we are trading gold, right? Gold is our underlying asset. And I'm looking at a call option. So my gold price at time 0 is S0. And my gold price at time T will just be S. I don't really know S, right? Because stock price is random. I can try to predict S, but X, I guess the change from S0 to S is kind of random. And on the market, I guess all the traders agree that the strike price of this call option will be K. So for a call option, I will enter, I guess, an agreement with someone to sell the product at time T with price K. So I think I have the payoff underneath. So I will only make money because I'm going to buy this product. I'm going to sell this product at K. But if the actual price is S, sorry, So I either make, so for a call option, I either make a profit, I guess, for S minus K or 0, right? So a call option only has a positive value when the actual price of the underlying asset at the maturity date is larger than the strike price. So basically, the final value of a call option is just a maximum between S minus K or 0. And for put option is exactly the same. But for put option, so the underlying asset will also have value S, and the strike price will also be K. But my payoff, I guess let's not say payoff, let's just say the final value will either be K minus S or 0. And that's what I have here. So basically, call and put, they will only have call will only have positive value if the underlying asset is actually larger than the strike price, and put will only have a positive value when the strike price is larger than S, right? Because that means I actually bought my put option at a price that is lower than the strike price, right? So in a way, I make money because I bought it in a lower price. And similar for call option, it means I am actually selling my asset, right? So if S is larger than K, it means I'm selling my asset at a price that is larger than the agreed strike price. So obviously, I also make money. So I'm going to spend a bit more time on put-call parity here, because the idea of put-call parity comes again in Module 10. But I'm just going to skip it for Module 10 and talk about it here. So basically, for call and put, so for put-call parity, let's assume we have two portfolios at time t0. And we want to look at what will happen to them at time t. So in my first portfolio, I have a put option, and I have the underlying asset at price S. So on the maturity date t, the underlying price here is S, yeah. Let's say it's S naught. So on the maturity date will just become S, right? And the put option will have, so the put option will basically have two possibilities, right? Sorry, let me change what I have here. So if K is larger than S, then the value of my put option will be K minus S. And then I will also plus my underlying asset, which has a value of S. So the final value of my portfolio will be K. But if S is larger than K, then my put option will have value of 0. And I still have the underlying asset with value S. So my final value will be S. So I know that the first portfolio, the final value will just be K or S. And obviously, it's going to be the larger one. And my second portfolio consists of a call option and some cash flow. Well, how much cash flow should I guess, buy at time 0? Let's just assume that the strike price of our underlying asset is K, and I'm going to discount K back to the present, and my cash flow will be K exponential negative R. So R is my risk-free rate, T minus T. Obviously here the lowercase t is just 0, so that as a maturity date, my cash flow grow to be K. For my call option, again, if K is larger than S, my call option will have a value of 0, right? But I have a cash flow of value K. So my final value of the portfolio will be K. But if S is larger than K, well, my call option will have a final value of S minus K. And I have a cash flow amount of K. So my final portfolio value will also be K. So the final value is also K or S. Therefore, we can say that these two portfolios are equivalent, which gives us the put-call parity here. So that's kind of about option pricing and what is a call and a put option. I think in the final exam, they either only ask you for call or only ask you for put option. Next, we'll move on to the Black-Scholes model. So Black-Scholes model, so here I didn't use price, right? So maybe pricing is not the right word to see here, because in this slide is actually just the value of a call option and the put option, but it's not their actual price. So Black-Scholes model is a way to price a call option or put option. And the value of, so we'll just take call option as an example. And basically, we have this very complex PDE, which we will learn to solve in Module 10 and Module 11, that will give us the value of C. So if we look at this equation, obviously, we want to know what is sigma square, and what is S, and what is R, right? Because the only unknown should be C, so that we can solve the PDE to get our C. So S is just our asset price. So again, if in the future is actually unknown, so sigma square is our implied volatility. Again, implied volatility is actually unknown. Usually R is known, so R is just a market risk-free rate, usually derived from securities of government bonds. And a T should be known as well, because European option has a maturity date T. So then we will have the boundary value problem with an explicit solution. So CST is equal to S N. So N is actually just the normal distribution of D1 minus K E negative exponential negative RT minus T times N D2. And this is how we define D1 and D2. I think how we come from the first equation to the second equation is quite complex, and we also need to assume that our stock price follows geometric Brownian motion, right? So only on the assumption of geometric Brownian motion, we can then get the expression for CST. So let's just take these things as granted for now, right? Because in this topic, we are trying to find the implied volatility. So let's just take these expressions for granted and come back to how we find them later. So let's focus on implied volatility. I'm just gonna double check if the live stream is working. Yeah, so we'll focus on implied volatility now. So in the real trading market, there are a few different types of volatility, such as future volatility. Well, it will be good if traders can know the future volatility, right? Then they can make judgment that ensure we never lose money. But that's just not the real case, because you don't know the future volatility. You know the historical volatility, but it could be unreliable because the market can be hard to predict. And you can also forecast volatility. But these three types of volatility, they are all actually volatility on the underlying asset or the underlying contract instead of our option, right? So we enter a contract to trade the underlying asset with the options, right? But all these three types of volatility is actually on the underlying asset, not on options. However, we want to look at the implied volatility, which is actually the volatility of the options, but not the underlying asset. And this is why, because the Black-Scholes model is on call option, right, or put option. Oh, by the way, if you want to change this formula to put, you can kind of just change the sign, right? Because call and put, like put is just the reverse of call. So if we have a formula on how to price a call or put option, and implied volatility comes from the call or put option, then we can just use what we have above to estimate the implied volatility, right? So you want your implied volatility to be a value such that the call option is the market price of the call option, right? Because then as a trader, you are not at disadvantage, because if the implied volatility gives you the market price of a call option, then at least you are not losing money or at disadvantage compared to other traders. So that is why we define F, right? So F is a function that we define in MATLAB, whatever, to be the call option price minus the market value of the call option, right? So the market value would be already given because it's just what is on the market. And we solve that to find our implied volatility sigma star. So there is a more detailed, derivation of, there is a detailed derivation of how we are sure that we can find a solution of sigma square. But essentially, I'm just going to very briefly, you want to show that the limit as sigma goes to infinity of f sigma is going to be larger than the limit as sigma goes to 0 naught of f sigma. And the crossover f sigma is equal to 0. And you also want to make sure that f dash sigma exists, and f dash sigma is larger than 0, I think. So if we have these two conditions, by IVT and the continuation of f sigma, we know that at least one explicit solution will exist for sigma star. So we'll look at this question from the 2023 final exam. And it's about drawing like a payoff diagram. I'm not sure if this year they're going to have the same question, because I think during the lecture we didn't spend too much time on payoff diagram. But I guess it's still a good exercise to do so that we understand call and put option. So basically here we are given a European style put option. And I also choose this question because it's on put option, and I think it's helpful to look at put option. And put option gives holder the right by non-obligation to sell the underlying asset, right? Because it sells the underlying asset, so we want the strike price to be larger than S, right? So that we sell it at a higher price, and we get money. We get something larger than 0. So here we are examined by a put option spread, which is a combination of one short position put option and a long position put option. I guess the language here is quite like trading terminology, but short just means you are selling and long means you are buying. And I guess one of the concepts people get confused is because in put option we are selling the underlying asset, and in call option we are buying And in put option, we are selling the underlying asset, right? And some people think you can only buy call option and only sell put option. At least that's the mistake I used to make. But I guess you can both buy and sell call option, and you can both buy and sell put option, because they are just like options are kind of separate from the underlying asset, right? So we can buy and sell put option at the same time. So they have the same expiry date and the same underlying asset. And we assume that the strike price of the one we are going to buy is larger than one we are going to sell. And this makes sense, right? Because like obviously the larger the K, the better for us. So you want to buy the one with larger strike price. So let VST be the price of the put option in the short position, and VLT be the price of the put option in the long position. And they want us to draw a payoff diagram to show how much money we can make. Okay, so let's just try to do this question. So I'm going to draw kind of the diagram separately, and then I can combine them together. So on the x-axis, they want us to have the price of the underlying asset. And obviously, I guess maybe an important value on the x-axis will be K. So let's do our short position first. Okay, and we know that for let's not look at our payoff first. Let's just look at the put option value. So for the final value of the put option, well, obviously if S is larger than K, it's just going to be 0. Maybe I should change another color. And if K is larger than X, then we are going to have a positive put final value. Now we are trying to sell this put option, right? So you actually want the final value of the put to be less than V of ST. The reason is if the actual value of this put option is less than the value we are selling, then we are selling it at a higher value, right? So we are actually making money. Hope the intuition that makes sense. Therefore, so the lower our put final value is, actually the more money we can make, right? Sorry, I'm just gonna check if I'm doing everything correctly. Yeah. Right. Okay, so this is going to be for our, I guess the put option we are selling. And let's now look at the one we are going to long, right? So again, here, this is just the final value for the put option. It's not really, and what they actually want us to draw is the payoff of the put option spread, right? So, but here is not the payoff. I'm just looking at the final value first. And for the long option, obviously, I still want to look at my strike price, and my strike price is going to be here. All right. And obviously, it's still the same put option. So the payoff is larger if S is smaller. And this is the final value of my put. And obviously, because I'm buying the option, right? So I want to buy at a price that is lower than the actual final value, right? So that I'm buying at a lower price. So if our put value is actually larger than our buying price, then we are actually making a profit, right? So we are making a profit, I guess, on the first half of our payoff diagram, and we are losing money on the second half. And for the short position, we are losing money if the put value is really large, right? So maybe let's use another color. So I keep losing money kind of at the beginning, and then if the put value become lower, then I'm actually making money. Yeah. Okay, so it's it's a bit hard to get our head around. So I'm losing money at the beginning, and then I start to make money. And this is my payoff for the short position. And I guess for the long position, if the final value is larger than our price, then that's good for us, right? So maybe at the beginning we are making money, and then we start to lose. And if we combine them together, we should get something like. So obviously our KX is smaller, and our KL is here, and this is S, right? So at the beginning, my short position is losing money, but my long position is making money. So maybe overall we have like a positive payoff, and then it kind of starts to go down, right? And until the end, we kind of start to get negative payoff. So this is the final diagram, and here is our payoff. So that's the solution to this question. Again, it kind of just examines our understanding of the put option and how does the put option's final value affect our choice of the put price, right? Because in real life, you have, like in a contract, you have multiple options. You have multiple choice for which value of for your put price, and you want to choose the one that maximum your payoff. Okay, the next section of this topic is on Taylor expansion. So it's about the forward and backward difference approximation. So I guess we just want to pay attention to how many times we can actually differentiate f, because that is going to be quite important. Hopefully, we are quite familiar with Taylor expansion at this stage. And in other math courses, we kind of ignore the remainder term, right? But I guess in this course, the remainder term is quite important because we want to look at the truncation error we will be making if we apply the difference approximation in MATLAB or Python. So if, I guess the general rule is if you only have f dash x, right, so if you only know the first derivative, then the remainder term is just OH, right, because here n will just be equal to 1. If you have knowledge on f dash dash x, then the remainder term will be big O h squared. And the reason is just, so n will be equal to 2 here, right? So the power of h largely depends on what number of order of derivatives we have. So we can use both x plus h, which means we have forward knowledge of x, or x minus h. So if we use the forward approximation, so again, these two methods are the same, right? So because both of them have the same error, which is OH. If we have the knowledge of x plus h, then obviously we will apply the forward approximation. If we only know what happened at x minus h, right, we don't know what will happen in x plus h, then we will use backward approximation. If we have both f dash x and f dash dash x, so for all the difference approximation, it's not too hard, right? So we just write out our Taylor series and we just rearrange so that f dash x becomes the left-hand side. And if we have f dash x and f dash dash x, then we can use a central difference approximation. And for all, and because we know what is f dash dash x, right? So our error will become big O of h squared. And because we know f dash dash x, so the central difference approximation work on both f dash x and f dash dash x. And the truncation error here is big O h squared. I just want to talk about one thing very quickly. So if you have OH squared plus OH squared, you will still get OH squared, because big O is just something that will goes to 0 as time or as n kind of progress, right? So if you have OH squared and OH squared is still equal to OH squared, it's not really 2 times OH squared. And then we will move on to the numerical method, I guess, or the iterative method. So basically the idea is we start with an initial guess x0, and then because we already have fx, and we even have f dash x, right? So using fx and f dash x, we can generate x1, x2, x3 until all the answer converge to a certain value x star. And ideally want this process to be quick and guaranteed convergence. I guess we all know how annoying it is if we need to run this loop for like 20 times, like in the midterm exam and through lab exercise. If you need to run like 20 times to get x star, then obviously it's quite computationally expensive. But I just want to highlight that it is possible that you will never get a converging answer if our initial guess is too far away, either from the left or to the right from the true answer, or if fx is just like a very complex kind of diagram. So because we are focusing on computational power or computing error of this course, so I guess it's possible they ask us something on the order of convergence. So basically, every time we do an iteration, we will have an error, right? And the order of convergence is the largest nu such that the limit exists and is finite. Hopefully, they will not ask us to kind of find the nu ourselves. Hopefully, it will just be something given. But we know that the larger value of nu, the faster the method will converge. Here we have a question from the 2016 final exam. And it basically says that if x bar is an approximation of the root x, and the error is 10 to the power of -6, then they want us to estimate error of after one iteration of the Newton method, which is quadratically convergent. So I guess we can just remember that Newton method is quadratically convergent. Again, the reason why the proof why it's quadratically convergent is given in the lecture slide. But even if you kind of just think about it, right? So beta is, so here we want to find, we already know that nu is equal to 2. And we actually want to know e to the power of k plus 1, right? Because we want to know the error after one iteration. So the first thing is we want to know beta, because the reason why we want to know beta is because we have this approximation that, sorry, let me, so we can have this approximation that the error of the k plus 1's iteration is approximately just beta times the error of the k's iteration to the power of 2. So obviously we just want to look at what beta will be. So you can just kind of remember that beta is equal to 1 if is quadratically convergent. And if you want to prove it, well, I guess it's quite intuitive that as k goes to infinity, beta will be 2, right? So even if you just look at the first and the second iteration, then beta is kind of 1. Okay, so if beta is 1, then for ek plus 1, so ek plus 1 will just equal to beta times ek to the power of 2, which is just 1 times 10 to the power of -6 to the power of 2, which is just 10 to the power of -12. And that's the answer for this part. So some of the iterative method, I guess first we'll have the Newton's method, right? Which means the k plus 1's guess of our true value is the k's guess minus fxk over f dash of xk. And this is quadratically convergent. We also have something called the secant method. So basically, secant method is used when we do not know f dash. So if we do not know f dash x, then obviously is we need to kind of approximate f dash xk. So f dash xk can be approximated by the secant method. This is pretty similar to how we find gradient in some of the lower math course. Obviously, secant method is less accurate than Newton's method, right? Because we are approximate x, but we are also kind of approximate f dash xk. So the order of convergence for the secant method is 1 plus square root of 5 over 2. Again, you can kind of just memorize this value. So if we kind of push the result of Newton's method to the higher dimensional, right? So if we don't look at x as a single value, but I want to know x kind of in a matrix, right? So this will be quite helpful in module 10 and module 11, in topic 10 and topic 11, because we want to know kind of the price of a put or call option at a range of st or a range of t. So I guess Newton-Raphson is just a generalization of Newton's method. So instead of solving one equation, we're solving a system of linear equations, and our error is gonna be all of these the distance of d squared, right? Because if it's one-dimensional, the error will be O of h squared. And then in higher dimension, it just become the 2 norm of d squared. And here, Jx is just Jacobian matrix. So if it's in one-dimensional, Jx is just f dash x. But here, because we are looking at multi-dimension, so we actually have a Jacobian matrix. And D is basically the same as H. D is just the vector, kind of the multi-dimensional representation of H. So I didn't talk about the optimal step size as a slide, but I chose a question on the optimal step size. Yeah, I'm not sure what question they are going to ask if they ask about numerical method. I mean, maybe they will just ask us to apply like Newton's method twice or something. But I guess the formula is quite easy to understand. So here, the question asks us to estimate the optimal step size h star in terms of relative machine precision epsilon when estimating f dash a. So basically, we just want to find h star in terms of our epsilon. And recall that epsilon is just equal to 2 times 10 to the power of negative 16. Okay, so I guess one thing I didn't really mention is the error in our approximation. So we will have 2 components of our error. The first one is the truncation error of H. Again, it's either gonna be OH if you only know F dash, or OH squared if you know F dash dash X. But we also have something called the relative error of H. And the relative error of H is actually given as O of epsilon of H. So it's kind of like the relative error in your approximation. And here we actually want to minimize E, right? So we want to minimize the total, maybe here it should be, yeah. So we want to minimize E, the total error, with respect to the truncation error and the relative error. And here, because we only have F dash A, right? We don't really know F dash dash A. So we know that our truncation error will just be O of H. And O of H is also an expression of H, right? So I'm just going to write it as C1 times H. Again, I don't really know what is C1, but I know it's just a constant, right? Because big O of H is just an expression of H. To minimize any expression, we just want to take the derivative and let it equal to 0, right? So for the relative error is big O of epsilon over H. And again, big O is just another expression of H, right? So I'm just going to let this equal to C2 times epsilon H. And I want to minimize my total error. So I'm going to find my first derivative of E dash, which is gonna be E1 minus C1 minus C2 epsilon H squared. And I'm going to let this to be equal to 0. Of course, you should always check that F dash dash X is larger than 0, so that when E dash dash larger than 0, so that when E dash is 0, we have the minimum value. And we should get that H will just be something and then epsilon. Yeah, I may just write out the whole answer. So I think H should just be C1 over C2 times epsilon to the power of a half. Again, it's just an expression of epsilon to the power of half, right? So it's just gonna be O epsilon a half. Sorry, maybe this should be the whole thing a half. And this is our H star. Right? So you don't really need any knowledge from iterative method to do this question. It's literally just minimizing the total error. But I guess this expression is quite important to memorize. And again, do not be overly confused by big O. Big O just means a linear representation in terms of H or epsilon over H. So that's everything for the first topic. And we are going to move on to numerical integration. So I guess the idea behind numerical integration or the quadrature rules is quite easy to understand. You basically just have, maybe I'll quickly draw all the diagram here. So we know what is fx, and we also have a few subintervals of x, right? We know what is fx, but we do not know how to calculate its integral. But we have some points, let's say from x, maybe 0, right? So x0, x1, x2, x3, blah, blah, blah. And we basically just draw out different, I guess, trapezium so that we separate our fx into discrete subintervals. And if is trapezoidal rules, right? So now we have different trapezium. If they say trapezoidal rules, you literally just calculate the area of each trapezium and kind of add them together. If they say the midpoint rule is less accurate, but we basically kind of find the midpoints between x0, x1, x1, x2, and x2 and x3. And we find the corresponding point from our fx, and we approximate based on our midpoint. So as you can see, instead of calculating trapezium, sorry, my graph is being messy here, but instead of calculating trapezium, we are actually calculating the areas of rectangles here, right? So obviously it's a bit less accurate because we have less rectangles. And we also have something called the Simpson's method, which is also the trapezoidal rule. But I think we have more subintervals. So Simpson's rule is more accurate. And for Simpson's rule, so obviously we want to calculate our x into different subintervals. From x0, I guess x1 until xn. But x0 is kind of just a starting point. And if we use the Simpson's rule, then our n has to be even. But I guess for the midpoint rule and the trapezoidal rule, n can be both even and odd. So here is a formula for the midpoint rule, the trapezoidal rule, and the Simpson's rule, right? So Simpson's rule does not simply take fxi and fxi minus 1 divided by 2. It actually uses something a bit more complex. And you can use quote fab, I guess, in Python. But usually you want to kind of create vectors of w and of fx in MATLAB or Python and kind of do the approximation yourself. So if it's trapezoidal rule, maybe I'll write it here. So for trapezoidal rule, actually, maybe I'll talk about this a bit later because I have a slide on this. Okay, we are just going to look at a question very quickly because I didn't mention the Gauss something notes. So the Gauss method is just a generalization of all the method I mentioned above. So basically, if we have Gauss, so the Gauss Legendre rule specifies that if I want to approximate from -1 to 1 of any function fx dx, so I can basically approximate this with a few points. Wi is the weight I give to each point, and f of Cassini I with I equal to 0 to n. Right. So this is a general formula, and we can actually apply this Gauss Legendre approximation to the Simpson and the trapezoidal rule. Right. So for the trapezoidal rule, UWI is UW as a vector. Sorry, it should be a vector. Is just gonna be 1 and then 2 and 2. And then until 2 and then 1. And then if you use the Simpson's rule, your vector is going to be 1 and then it's going to be 2 and then it's going to be 4. And then it's going to be 2 and 4 and 2, and until the last one is 1. Yeah, so Simpson's rule is being more accurate, but the weight we assign to every second point is 4, not 2. And it all comes from the formula of Simpson's rule. So after specifying our vector W, and then we can find out our f of Cassini I, where Cassini I is just, I guess, x1. It's just like you separate x to x1, x2, and xn. So Cassini I here should just be xi. But sometimes Cassini I can be defined differently. And I think the general rule is you want to make sure that the midpoint of all your Cassini I, right? So the midpoint, if we are valuing integration from -1 to 1, then the midpoint of all the Cassini should be 0, given we are using an even, given n is even, given we are using an even number of points. I think the kind of challenging part of this question is we actually want to evaluate this integration from 0 to t. But for this Gauss method, it only works from -1 to 1. So you want to think about how you can apply something you approximated from -1 to 1 to something 0 to t. And it's not overly hard. You basically just apply the formula I wrote here. It's still I equals 0 to n, and we have wj, right? So again, in this question, we assume we know wj, so you don't need to specify wj yourself. And we know zj, right? So you don't need to specify zj yourself. You just assume they are given. And obviously, each each Cassini I, Cassini j, again, you want to make sure that the midpoint of all your Cassini j is 0, right? So you can let your Cassini j to be equal to zj plus 1 over 2. And then we need to multiply that by t, so that our final approximation is for time t, not just from -1 to 1. So we also have something which, again, push the results we just talked about into multidimensional, called the tensor product rule. So we start with one-dimensional quadrature rule, right? So which is the rules we just talked about, the trapezoidal rule or the Simpson's rule. And we have defined weights Wi and Zi. And now we want to integrating a multi-dimensional function that is in d-dimensional. So we just recursively apply the one-dimensional quadrature rule. I don't know how to. So basically, you start with fx1 dx, right? So you start with fx1 dx, and you approximate fx1 dx with wj and wj and zj. Okay, so you get your first integral, and then you also need. Maybe I should start with xd. Sorry. Well, I guess it doesn't really matter. So I can start with xd, right? So I approximate the integral of fxd dxd using the quadrature rule with predefined wj and zj. And now I have d minus 1 dimension to work with. And I apply the quadrature rule on xd minus 1 again. And now I have d minus 2 dimension to work with until you converge to something like the sum of capital G, wg, fxg. And the number of terms in the summation is n to the power of d, which is quite, I guess, intuitive to understand, right? Because you have d-dimensional, and in each dimension you have n points, so you just n times n times n times n until you get n to the power of d. I will talk about curse of dimensionality first. So I guess they can't really ask you any numerical question on the curse of dimensionality, so it's mainly just kind of explain what it is. So in real life, we do need to apply tensor product rule more often. I think especially in machine learning kind of example, or in some trading context. But the problem is the total number of points we need to apply the tensor product rule is n to the power of d, right? But usually the number of d can be larger than n. So basically you will have a non-symmetrical matrix in each dimension. And the number of total points we need, not the number of d will larger than n, so it just the total number of points we need, so capital N will be very large. And sometimes we need a lot of points, so the capital N is very large, but we only have a limited dimension d, right? So this is what we call the curse of dimensionality. So n grows very fast with d, right? So even in two-dimensional, you need like a lot of points, but you actually don't have that many points. So when the dimension become too large, your approximation just become very, very inaccurate, because you actually don't have that many points to tell you what the approximation truly is. However, the curse of dimensionality only applies if the total number of points we need depends on the subinterval points, the lowercase n, in each dimension, and our total dimension d, right? So that is why in real life we also need the Monte Carlo method. Again, Monte Carlo method is the next topic. I kind of messed up the order of question here, but let's just look at Monte Carlo first, right? So Monte Carlo basically means you simulate capital N, you solve, right? So intuitively understanding, does Monte Carlo method suffer from the curse of dimensionality? So even from an intuition perspective, the answer is no, because you kind of just simulate the points you solve, right? So the number of points you can simulate is not restricted by dimension d. But I guess statistically, the rooted mean square error of Monte Carlo method only depends on sigma f, so the standard deviation of our function f, and the capital N to the power of -1/2. But again, n can be determined by yourself here. So this routine mean square error is not directly dependent on t, right? So our error is not dependent on the dimension. So we do not suffer from the curse of dimensionality. But in a lot of other methods, when the dimension matters, right? So here, obviously, the tensor product rule, the dimension definitely matters. And then we suffer from the curse of dimensionality. So for this question is on the degree of precision. So again, quadrature rule just means any of the quadrature rules we have above. So for any of the quadrature rules, the degree of precision m can be calculated as the sum of weight wi times p of ci, right? So it's still this formula here, but instead of f of ci, we have p of ci. I may just come back to this example after talking about Monte Carlo simulation, because this example is more about the degree of precision on Monte Carlo method, but not the quadrature rule. So p is just a polynomial. So after talking about the curse of dimensionality, obviously we want to find ways to simulate random numbers so that we do not suffer from the curse of dimensionality. And this comes in the topic of random numbers and simulation. So just two quick revision on the types of random numbers. So usually we want uniform random numbers and normal random numbers. I guess ideally we want to be able to have to generate x1. Maybe I should use this one. Maybe this is a bit brighter. So ideally, we want to have x1 until xn from a distribution. And we know that this distribution follows the CDF of capital F. So ideally, we want to be able to generate x1 of xn with any given f. But to simulate x1 to xn from any given f, sometimes we also want to simulate just random numbers first. So first one is uniform random variables. Random numbers. Sorry, they are numbers, not variables. From a given range A and B. So hopefully we already know the concept of uniform distribution and normal distribution from second year maths. And basically the probability of x equal to x in a range of A and B is just 1 over B minus A. And the expected value is A plus B over 2, and the variance is B minus A squared over 12. Well, in reality, sometimes we only generate x that follows uniform 0, 1. But we want y that is from uniform AB, right? But we may only be able to generate from 0, 1. The good thing is for uniform random numbers, we can apply a linear change of variables. So we can generate x and let y equal to A plus B minus A times x, so that y follows uniform random distribution from A to B. And if you want to generate x in R, you can use something like R uniform. I couldn't really remember. I think it's also R uniform in MATLAB and Python, but not entirely sure. If you do maths 3821, hopefully you learn a bit more about why the linear change of variables makes sense. And similarly, for normal random numbers, we want to generate something from n with expected value mu and sigma square variance, right? So this is kind of the PDF, the density distribution of y, and we know that the expected value of y is equal to mu, and the variance of y is equal to sigma square. And again, in real life, most of the time we can only simulate x from normal 0, 1. And we want to apply a linear change of variable on x so that we have y is from normal mu sigma square. I may just quickly write down the linear change of variable here. So the linear change of variable should be something like y is equal to mu plus sigma x, I think. Yeah. Again, you can kind of prove this by using the density distribution. And this is also true in multivariate, right? So when x is multivariate normal, then you can also apply y equals mu plus sigma x so that y follows mu sigma square. So we'll talk about Monte Carlo method. So I think the important thing that the lecture kind of repeated over and over again is in Monte Carlo method, x is indeed a random variable, right? So x is unknown, and let's not say x, let's just say any number xj is a random variable. And we want to compute multidimensional expected value, right? So again, say if we have stock price, you want to know that in a given period of time, what is the average of our stock price? And then you can decide if you want to buy or sell or do whatever with the trade, right? So sometimes we just want to know the expected value of our random variable. And our random variable follows a distribution of fx. I think we can assume f is given here, and px is so fx is a function of x. And px is the density distribution. Is a density distribution of x. We know what is fx, but we can't really just calculate the integral, right? So one way is we can simulate a few values of fxi, right? Because we know f, and we just take the sum and divide them by n, so we get the mean, right? So it's kind of the empirical mean of a distribution. But obviously, we want to know what is xi. Right, so we want to first simulate random numbers x1 to xn from the probability density distribution px, then calculate fx1 to fxn, and then take the mean. I guess we can assume that px will be given as well. So how do you generate x1 to xn? Is usually just from uniform distribution or normal distribution. Obviously, again, this course is about computing, right? So we have simulated the mean, but how do we reduce the variance in our simulation? Because if the variance is too high, it means our estimations may not be accurate, right? So basically, the key idea is we want to choose a function g. Again, you kind of want to determine the function g you solve that is reasonably close to f. And the expectation of g is easy to compute. I guess if G is normal distribution, then you know the mean is just mu. Right, so you want to find G such that the expectation is easy to compute, not some like really complex integral you can't even solve. And then we want to use the approximation that expectation of F is just expectation of G plus 1 over n of this thing, right? So this is kind of the variance. Maybe here should have a square. Let me check very quickly. Okay, it's not square. It's actually just the empirical expectation of fxi minus gxi. But we want f and g to be close, so that the variance of fx minus gx is at least less than the variance of fx, right? So that we reduce the variance in our simulation, especially with RMSE. Quasi-Monte Carlo method is when xj is not a random variable. Again, I think the lecture, for whatever reason, kind of emphasizes a lot that xj is not a random variable. X is a random variable in Monte Carlo method. Xj is not a random variable in quasi-Monte Carlo method. That is why it's called quasi, right? Because it's like they aren't actually random numbers, but we kind of manipulate them so that act as random numbers. Maybe there will be a final exam question on this. Maybe that's why he kept emphasizing. I'm not sure. But basically, we already have x1 until xj, right? So Monte Carlo, we still want to simulate x1 to xj. That's why they are random. But in quasi, we already have x1 to xj. So for quasi-Monte Carlo method, the end goal is actually to reduce the discrepancy in our simulation. And obviously also achieve, I guess, a balance between error in computing and the efficiency of computing, right? So quasi-Monte Carlo want to increase the efficiency of computing as well. So we focus on reduced discrepancy. So we have something called dn, which, so you basically, you will have like, you will have a few, I guess, so you have like y1, but y1 is a vector. Sorry, maybe I'll use capital here. So you have y1 until yn, but y1 until yn are also vector, right? So you have y in 0 and 1 in d-dimensional. Sorry, let's use d here, not n. Sorry, let me just write this a bit more nicely. So we have y1 until yd, and each of them is a vector. And we also have x11, x12 until x1n. And we keep doing this until it's xd1, xd2, and until xdn. And we just want to look at the discrepancy between y and x that is in 0 to 1 for each dimension over n. This is what we call the star discrepancy. If you done like statistical inference last term, I think this is quite similar to one of the empirical methods we learned in that course. But we just want to focus on what the superior between our yi in each dimension and the number of xj in that area. So this is from 2023 final question 3 part I. So first part kind of help us to understand how simulation works. It asks us to show that the random variable f inverse x, right? So again, why f inverse x is a random variable? Basically because x is uniform random variable, so you don't really know the value of f inverse x, and it has distribution with log f. I think this question, the phrase of this question is a little bit weird, but essentially we just want to look at the distribution of f inverse x first. So we want to look at the probability that f inverse of x is going to be less than or equal to y, right? So I just use y here because it really can be anything. And this is, by definition, this is the distribution of f inverse x, right? By definition, this is the CDF of f inverse x. Because f, right? So f as a CDF is monotonically increasing. So if I apply f on both sides of my inequality, the inequality will still be true, right? So we'll just have the probability of f inverse of x is less than or equal to f of y. But f and f inverse pretty much cancel out. So on the left-hand side, we'll have x, and on the right-hand side, we'll have fy. Okay, but x is a uniform random variable, right? And in 0 and 1. So basically, if, I may use another color here. So if x follows uniform 0, 1, then the probability that x is less or equal to a random number x is just x, right? But given that x is between 0 and 1. Okay, so here we can just conclude that the probability x is less or equal to fy is just fy. So we have shown that f inverse x as a random variable actually follows the same distribution as fy. And that is all part A is trying to ask us. Part B says, suppose we have a procedure to generate sample x1, x2 for x. How can we use these samples to generate samples from y? And what is likely to be the practical difficulty? So if we already have x1, x2, right? And we know that, so from part A, we know that fy is actually just equal to f of f inverse x of y. So again, f inverse x of y, hopefully my notation isn't confusing you guys. So this thing is just the same as this expression. And we already have x1 and x2 from x, right? And then we can just apply that to our f inverse of x so that we generate samples that follows fy. Does that make sense? Yeah. Because x1, x2 is from fx, so that we also have f inverse of x, but f inverse of x follows fy. So I guess as long as we apply f inverse on x1, x2, we actually generate samples from fy, right? So we generate samples by using f inverse of x1, f inverse of x2. The practical difficulty is just most of the time you can't really compute f inverse. I guess unless f is standard normal distribution or like exponential distribution, you can kind of compute f inverse. But if f is a very complicated CDF, the difficulty is to find f inverse. And that's everything in random numbers and simulations. I'm just going to get some water, but I will be back in 2 minutes for stochastic integration and SDE. So let's keep going with stochastic integration and SDE. I'm probably going to go over time, but that's okay. This part is a bit long, but I really like the topic of stochastic integration and SDE. It's very interesting. So basically, we start with the idea of random walks, right? And the reason why we need random walks is just because you can't really predict your stock price if they are going to go up or down, but you assume that the movement is random, right? You don't assume there's any trend or seasonality in your trades. Sorry, I guess not in your trades. In the underlying asset price, right? So again, your underlying asset can just be equities or stock price, and you don't assume there's any trend in their movement. You assume their trend is random walks. So basically, random walks, it just means that every day, your stock price can go up with probability a half or go down with probability a half. And we want to look at the discrete increment, right? So I think it's very important if you want to revise stochastic integration and SDE, it's very important you kind of get the whole picture, right? So eventually we want to we want to predict our stock price, how will they go, and then price our put and option, or then choose our contract. But we actually start with discrete case, and then we move into the continuous case, right? So it's very important you start with the discrete and then move into continuous, because if you just directly go into the continuous case, you will get quite confused. But if we just say that every day we discretize, we assume that stock price are discrete, every day they go up or they go down with certain probability, then we have a random walks. And we want to focus on the increment of our random walks, which is just your stock price for the next day minus your stock price for today, or xn plus 1 minus xn. Hopefully, a lot of us here have done stochastic process last term, so we kind of know what is random walk. And then we also have the form. We assume that the delta xn is equal to mu times delta t plus sigma times delta t to the power of gamma times zn. I guess maybe I should talk about the intuition behind this. So basically, xn is our stock price, and by assumption, we assume that xn is log normal distribution. And with parameter mu, so the expectation of log xn. Sorry. Yeah. Let me just write it down below. So I assume that my stock price xn follows log normal distribution. Parameter mu and sigma square. What this means is the expectation of my log of xn is equal to mu. And I think the variance of the log of xn should be sigma square. I did prepare the slide and everything in a rush because I have too many exams next week. So if I'm wrong here, don't blame me. But I think this is the definition of log normal mu and sigma square. So that's why xn will just be mu t plus sigma times t to the power of gamma times zn, right? So zn is our standard normal distribution. I may just write it here because that is quite important. As in why xn is log normal, not normal, it's just because like xn is stock price, right? And stock price can't be negative, right? So it's just easier if we take the log of xn. And it's just easier to calculate as well, because if you think about x being the log, then the difference is kind of just log x n minus 1, n plus 1 minus log of xn. And the change, the increment still depends on a standard normal, right? But standard normal can be easy to simulate from what we talk about above. So that the expectation of xn minus x0 is just n steps times mu times the difference in t. Again, we use delta a lot. It's just because we are looking at discrete steps here. So if we know x0 is equal to x0, which is usually the case, right? Because x0 can be your stock price today, and you already know the stock price today. You want to simulate in what happens after n days. And then we can say that our expected value of xn is just lowercase x0 plus mu times t. And if our gamma is larger than a half, then the variance will actually approach 0. And so this is as delta t goes to 0. If our gamma is a half, then the variance of xn minus x0 will be sigma squared times t. If gamma is very small, then the variance just goes to infinity. Okay, so that was on random walks. I guess maybe I shouldn't put everything here. Maybe I should put things here below, right? Because now we are moving from random walks to Wiener process. So Wiener process is just random walks, but in the continuous case. So if we have a stochastic process Wt, again, stochastic just means W depends on T. In the interval 0 to T, we say Wt is a Wiener process if we satisfy the 4 points below. So you do want to show that if a question asks you to show WT is a linear process, you do need to show WT satisfy all four conditions. Hopefully, exam doesn't ask us to prove something is a linear process. So basically, we want to show that WT depends continuously on T for T between 0 and T. You don't really need to show anything for this condition. It's just like naturally satisfied by definition. But we want to show that W0 is 0, right? So we kind of start with 0. And I think we also want to show that the expectation of WT is 0. The reason is if you think about random walk, right? So if you think about a drunk man goes to like north, east, south, and west with equal probability, eventually he's just going to go back into the original point, right? So the expectation of the linear process should just be 0. We also want to show that WT minus WS, so T and S is just two random points in our interval. And we want to show that WT minus WS is also a normal distribution with mean 0 and variance T minus S. So we want to show that the variance does not depend on 0 or capital T, only depends on the time points we choose. Oh, maybe here shouldn't be WT equals 0. So we just want to make sure that WT minus WS is 0, which is just what I talk about below. And we want to show that any 2 points T and S and any other 2 points U and V. So if we only look at the linear process from S to T, and the linear process from U to V, they are independent of each other. And then from linear process, we go to even more complicated case, right? Because linear process kind of assumes that WT minus WS has a variance T minus S, and each 2 points are independent of each other. And then we want to move on to Ito integral, which is actually, we add an actual function from linear process, right? In linear process, there's only WT. But for Ito integral, we want to look at F, that is in terms of WT and T. Again, even if you learn Ito integral many times, you still get confused. Because WT is a function itself. And now we want to approximate WT with another function of F, right? So obviously, if you want to integrate F with respect to dWt or dt, you kind of want to look at WT as well, and then look at F of WT, right? Because WT itself is a stochastic process, but FWTT is also a stochastic process. Luckily, I think this course doesn't go into that much of depth for Ito integral. We essentially just want to learn how to approximate Ito integral using computers or different numerical method. So let's define delta t to be the total time over the steps we have n, right? So again, this is kind of like a discrete form of Ito integral. So we kind of separate the continuous time into n sub-intervals and define Tn to be n times delta t. So in other words, Tn is just equal to n times t over n. Obviously, you want to I think the question will pre-specify to us what is n, what is capital N and lowercase n, and what is capital T. And by definition, right, so this is actually just the definition of Ito integral. It's just, we look at this function f in each interval, right? But each interval is like a linear process. Yeah. And then from Ito integral, we go to an even more general case, which is stochastic differential equation, because only after we learn stochastic differential equation, we can then approximate our Ito integral. Again, as I said before, f is in terms of WT and T, right? So you want to look at xt in terms of dt and dwt. The initial condition is x0 is a given value. Because if you don't have an initial condition, you can't really get the result for your integration. If we apply integration on both sides of the equation and sub in our initial condition, we can find the integral form of xt, which is just the initial value x0 plus fx with respect to ds from 0 to t, and gxx with respect to dws from 0 to t. But again, dwx itself is a stochastic process, right? So a lot of time you actually can't find an exact or explicit solution for xt. It's just very hard to compute this integral. But that's the definition of SDE. We also have Ito's lemma. So Ito's lemma just tells us that if yt is equal to h of xtt, then the derivative of y is will differentiate h with respect to t plus a half of g of xt square of derivative of the second derivative of h with respect to x times dt plus dh dx of dx. I think the issue here is we didn't really talk about what is g, right? But essentially g is usually a function that is given to you. Yeah, there's much more we can talk about Ito's lemma. There's also like proof of Ito's lemma if you are interested. But I guess it's not really a key focus for this course. And now, combining what we know about Ito integral, Ito's lemma, and SDE, we come to geometric Brownian motion. The reason why we need geometric Brownian motion is because this is an assumption we use for Black-Scholes. So basically, Black-Scholes start by proposing asset price obey a geometric Brownian motion. And also, geometric Brownian motion just means xn actually follows log normal distribution, as I already mentioned before. And then we can price our asset price. Again, this is our asset price ST, right? It's not our option price. Given S0, and then we kind of apply the log normal distribution on T and WT to get our ST. Again, the proof is quite complex, but you can kind of have a look yourself if you want to. So let's look at an example from last year's final exam, which is question 3, part I. So we have stock price ST assumed to follow geometric Brownian motion. So here is the, I guess, the normal form of ST. We can also write geometric Brownian motion in terms of the derivative of ST, which is actually in terms of dt and dwt. And it's actually quite nice because we don't have, like here, we only have mu and sigma. We don't have a term that is dependent on t, right? So this is what we call a driftless process, I think. So Brownian motion is driftless. So WT is a standard Brownian motion. Mu and so standard Brownian motion is just a Wiener process. I hope I remember this correctly. Mu and sigma are positive constant, and S0 is given. I think we can also assume that mu and sigma are given. And the question asks us to describe, right? So you want to have some details how we can simulate asset price path, right? Again, we only know S0. We want to know ST0, ST1, STR, and this is only the J's path, right? So you actually want to, what you actually want to simulate in real life is from 1 to j. We have st0, 1, st0, 2, until st0, j, which is like the possible path SI price can be at time t0. And then we want to have st1, 1, st1, 2, until st0, st1j. Maybe it's the other way around. Sorry. Sorry, my handwriting is really bad. Let me see. So I think you want to have st0 of 1 and st1 of 1, and then str of 1, and then you want to have st0 of 2, st1 of 2, until str of 2. And then you kind of keep going, right? So you actually want to get like a n by n matrix. Remember this because we are going to talk about this matrix in the next topic. That's why I want to briefly mention it here. But it has nothing to do with the question, because for the question we are looking at only one path, which is the jth path, for j equal to 1 to n. And t0 to tr is obviously between t and 0 and t. And it actually gives us a hint, which is we can use the discretization. And this is what I mentioned in the random walk slide. I think this question looks a bit overwhelming, but if you think about it, right, it's kind of just, I don't want to say it's like approximation. It's kind of like you just write a for loop, start with S0, and you keep it running. Maybe I can kind of mention the algorithm here, but I guess the question only says describe. So we don't really have to like describe an algorithm. And again, we already know mu, we already know sigma, right? And although we don't know z, but z needs to be like realized observations, right? So if I'm going to do this question, the step 1 I'm going to write is simulate, I guess like z1 until zr from a standard normal distribution. At least is something I wrote down, right? Because we know that z follows normal 0, 1. Again, this is just from the slide above. The slide here. And then basically, this is just discretization of this formula. So step 2, I need to calculate my delta t, which is actually just t2 minus t1 equal to tr plus 1 minus tr for any r, right? So that I have these two things. And then I want to look at I guess st2, I guess maybe let's start with st1 minus st0, because st0 is what we know, over st0 is equal to mu of delta t plus sigma times delta t times z1, right? And then rearrange the equation. So I'm going to skip all the detail here. Rearrange to get st1. And just repeat this process for, so step 4 will be repeat to get st2 AEST. Yeah, so it's basically like describe your for loop in MATLAB. Hopefully this makes sense. The last part of topic 10 focus on, again, we kind of come back to Black-Scholes, right? But in topic 7, when we talk about Black-Scholes, it's mainly about finding implied volatility. But now it's actually about pricing. And let's just look at call option as an example. So again, you don't really need to remember this formula. I guess you can always put it on your formula sheet, or it will be given in the question. But this is just Black-Scholes, right? So V is the option price. R is a risk-free rate. S is asset price. Sigma is implied volatility. So for call option, if S equals to 0 at time t, then call option will just be 0, right? This is kind of obsessive. Who would pay to buy a call option if the asset price is 0? So if the asset price goes to infinity at any point, then our asset price can be approximated by S minus K e to the power of R times t minus t. If at maturity date, then C is just equal to the maximum between S minus K and 0. Again, this is like what we talk about above. And for put, it's just the other way around, right? There's more, I think there is a proof about why this is the case and why these are the case on the lecture slide, but I'll just skip the proof here. And this is again just about how to value in call options and put options. Here should be P, not C, sorry. You probably think that we still don't really know how to price any put and call option, right? Like we have this formula, but if we can't really find an exact solution, we kind of have the approximation. But especially for any time between 0 and t, I guess that's more like a practical trading thing. It's like between t, so between 0 and capital T, I want to buy or sell a call option. I want to buy or sell a put option. I want to buy or sell multiple call and put option, right? So I want to have like a portfolio of call and put option, and I want to buy and sell them. How should I choose? What price of call or put should I choose? And just by giving this formula, we still know nothing, right? But we are going to talk about some finite difference method in topic 5. So obviously the things we want to know most is Vj at any time j at n minus 1 or n. So this is an explicit method, which means you can actually get an explicit solution. Again, in the lecture, he did spend a lot of time talking about why we can get an explicit solution. It's basically, if you look at this formula, right, the only unknown is Vj to the power of n. We know Vj minus 1. We know Vj n minus 1. We know Vj plus 1n. The only thing we do not know is Vj of n, I think. And that's why if we only have one unknown, then we can definitely find an explicit method. Sorry, give me one. I'm going to double check if, I'm going to think about if it's Vj or sorry, is Vj n minus 1. Sorry. I probably talk for too long. It's Vj n minus 1. The reason is maybe I should talk about the intuition behind the finite difference method first. So it's just like, again, the intuition is I want to know what will happen when my time is between 0 and capital T, right? So that I can better manage my portfolio. So basically, my option price V is depending on S and T at any given time between 0 and capital T. And the asset price is going to be between 0 and Sn. Okay, and I'm going to divide them into a grid. Okay, what do I know about this grid? Is quite interesting because the things I know is actually the last line, right? Because in the last line, I will have my asset price, I'll have my maturity date, and also have my strike price, right? So as mentioned here, at time t, I actually know the call price will just be 0 or S minus K. Similar here, at time t, I actually know my put price will be K minus S or 0. So I actually know everything at capital T for all the different asset price, right? Because no matter what the asset price is, let's say Sn of J, Sn J minus 1 until like Sn1, no matter what the asset price is, my V is always going to follow these two formula. And I also have some knowledge at time 0, right? So I know the different asset price at time 0. So what we actually do not know is just between, which is why we actually know Vj of n because it's at time n, right? Anything at time n is actually already known. But anything before time n is unknown. If we only have one unknown in our equation and we have one equation, then surely we can find an explicit solution, right? And we have alpha j, beta j, and gamma j. Again, there's more detailed derivation in the lecture slide, but that's what they mean. Again, we can kind of find delta S and delta S squared, right? Just using the description here, right? As long as we know T0, we actually can find ST1, ST2, and we can calculate delta S. Because delta S is just a change in S. However, the problem with explicit method is the instability. So the explicit scheme is only stable when the ratio of delta T over delta T, S squared is smaller. And the reason behind this is I think the thing is only stable if I think it is only stable if alpha j plus beta j plus gamma j is less than 1. And after some numerical manipulation, you will get the fraction here. So we actually can't really use explicit method that often, even though it's a preferred method, it actually become very unstable. And if you want to look at what it feels like to be unstable, you can try like the last tutorial, the last lab exercise. The implicit method is we do not have a definite solution. The reason is we actually do not know, so we don't know n plus 1 of j. We actually also do not know, I guess, I think this, yeah. Yeah, so is called, maybe, sorry, I think the expression here is not that correct. Yeah. Yeah, I think yeah, the reason is we don't know Vj to the power of n plus 1, right? Because we kind of only have knowledge of n. And we also don't know what is Vn j minus 1 because it happens before, it's like the step before. The only thing we know is Vn of j, and I think Vn of j plus 1. Yeah, so we definitely do not know Vn of j minus 1. And we definitely do not know Vj of n plus 1. So we have like at least two unknowns. Therefore, we do not have an implicit method because we have like two unknowns. And we only have one equation. And again, this is the expression for alpha j, beta j, and gamma j. So at each time step, we actually have to solve NS linear system. And A is a coefficient matrix. It is tridiagonal, right? Because it depends on j minus 1 and j plus 1 and j. It's not symmetrical because it's not Topliss and it's independent of n. So it's actually just quite hard to compute. But I think implicit method is always stable, right? So again, I'll refer you to lab exercise 10, like the last week's lab exercise. So implicit method is always stable. And I also recommend you to actually have a look at the script. So in the lab exercise, they directly give us a script for implicit and explicit method. But I do see past final exam paper actually ask us to write down the algorithm. So highly recommend to actually look at the script for the two method. So you kind of know how to write the algorithm. It's just a bunch of delta t and delta s and delta s squared, right? We know how to find delta s. We know how to find delta t. Then we will have alpha j, beta j, and gamma j. I think he said the CN scheme will not be in the final exam. But it's essentially just another finite difference method where we kind of approximate the interval of n plus a half and then apply the Taylor expansion. So it's a bit more complex than the first two method, but it's kind of the same intuition. So I may just skip CN since it will not be in the final. Is it not in the final or in the final? Let me double check. Yeah, he said CN will not be in the final. So we want to look at the accuracy of each method. So both explicit and implicit approximate PDE to order delta t plus delta s squared, right? Like you can just directly tell from the expressions. And we have the big O of delta t and the big O of delta s squared, provided that the scheme are stable. Again, the big O comes from topic 7 when we talk about the precision and the truncation error, right? So if t is only delta t is only 1 times difference, then the truncation error is also just delta t. But if it's s squared, right? So the highest order is squared, not just s. Then the big O is just big O delta s squared. So usually, as I said at the beginning, the last question of each year's final is always Black-Scholes. But it kind of combines our knowledge in topic 10 and topic 11. So it asks for simulation method or describe the algorithm of explicit solution. Sometimes it asks about topic 7 as well, right? As I shown at the beginning that put payoff diagram. So this question, I mean, I think 2020 is like they probably have it, or maybe it's term 1, so it's still in person. But I think this question is not that hard. It just has a lot of different components. So let's have a read together. I'm just going to go over time for like 20 minutes. Yeah. So they give us, so here we are going to look at the value W of an option, right? So again, W here is just equal to equal to V, sorry. They, for some reason, use different notation, but W is the value of an option of an underlying asset with price R, right? So R is equivalent to S. They just use different notation here. So we still have V, S, and T. And we have the Black-Scholes equation. Again, they just change V to W and S to R. Nothing crazy here. We already know risk-free rate R and volatility sigma, right? So we assume they are known. And we want to use this to price a put option. Again, it actually does matter for if we are using call or put, right? Because for put, at capital T is equal to the maximum of K minus S or 0. The strike price here is L, sorry, not K. I don't know why they said carefully explain. I don't know if carefully kind of takes any percentage of mark, but I guess just try to explain as much as we can, right? So what the initial conditions are for this problem and what is the boundary conditions are. I guess when they say boundaries, they kind of talk about when T is equal to T. From my understanding, initial condition kind of also count as boundary condition, right? So maybe T is equal to 0. So this again comes back to what I have on this slide, right? So we just want to look at the cases and the corresponding put option price. Okay, so the initial condition is at time t equal to t, right? Why is it initial condition, but t is equal to t? Because as I draw here, we actually start with the maturity date. We actually start with t, and we jump back to t minus 1, we jump back to t minus 2, and so on, right? So the initial condition, that's why they have a quotation mark, right? Because the initial condition is actually the ending condition. Sorry, where am I? Yeah. So at time t equals to t, W is to be maximum of L minus R if L is larger than R or 0. But for boundary conditions, I guess maybe I shouldn't say t is equal to t here. Is more as t goes to infinity. And when t is equal to 0. So when t is equal to 0, W should just be L, the strike price, exponential negative R t minus t. And when R goes to infinity, the put option goes to 0. The second part of this question says that the change of variable to log moneyness, what is that word? I don't really know. And time to expiry. So basically, S is just the log of R over L, right? So it's just a log of our option price over our strike price. And tau is just t minus t, right? So tau is actually the time we have until maturity. So again, nothing really crazy here, right? So everything is what we have learned. which gives that W of RT is equal to V of S tau, which is equal to, so R is L times exponential S, T is capital T minus tau, right? Because tau is equal to T minus lowercase t, so obviously T is equal to capital T minus tau. Anyway, it doesn't really matter. Question A asks us to find the expression for dv tau, dv ds, and d square v ds square. You shouldn't kind of, so I didn't really talk about Greeks, because like I think he also said he won't really ask for Greeks. Hopefully not. But essentially, so tau is a time here, right? And if we look at dv d tau or dv dt, it's actually just Greek of theta. And I think S is not really R here. If S is R, then dv ds is delta, but I'm not going to write anything. And d square v ds is gamma, right? If S is just the asset price, if S is asset price, maybe I'll just write it on the side. Actually, it doesn't, yeah. I'll just refer you to the last part of lecture slides for the Greeks. But we want to find these expressions, right? We know what is tau, we know what is S, and we know what is S square. So essentially, we just want to look at V in terms of this and find the derivative. But the only thing is we don't really know V, right? I mean, V is some sort of Black-Scholes transformation. But we can't really find the explicit for V. And part B asks us, actually, let's just look at part A first. So basically, we don't really know the specific expression of V. So dv d tau is just when you differentiate tau in W of R and T minus tau. Nothing crazy here, just change V to an expression of W. And because tau is negative here, so this is just equal to negative dw dt of R and T minus tau. And obviously, we want to show that we can kind of approximate. Actually, I think that's just the solution. I don't think we need to do anything more here. Essentially, just a change from V to W. Here is the same. We just change from V to W. But we don't really know ds. And we can do dw dr first, and then dr to ds. I guess we just let R to be equal to L times exponential S here. So R here is still just equal to L ES. So that we are left with an expression in terms of dw dr. I guess it just makes the derivative easier. And then we can just do it again for the second derivative. Part B asks us to show that the Black-Scholes is equivalent to the expression here in terms of S and tau. I guess the first part helps us, right? Because we already found dv d tau, dv ds, and d square ds square in terms of S and tau. So we can just kind of sub in the expressions. And then it asks us to look at the initial conditions and the boundary conditions for the transform problem. Okay, I think this is a good question, but it doesn't really require any knowledge. We just want to look at the limit, because initial condition is just what happens to the expression when small t is equal to capital T, right? Yeah, or when tau is equal to 0. And then it also asks us for the boundary conditions, which just basically want us to look at what will happen if t goes to infinity or t minus tau goes to infinity, and when t is equal to 0. And I guess it doesn't really change anything, because at the end of the day, the maximum payoff, so the value of the put option is still going to be 0, or your strike price minus R, right? But we just don't want to look at R here, we want to look at S. But R is just, so S is equal to log of R over L, right? So R is actually just exponential of S. And because S is equal to log of R over L, and tau is equal to T minus capital T. So if R is 0, when S goes to, so when S goes to negative infinity, obviously log of R over L will also goes to negative infinity, which implies that R goes to 0. Well, if R goes to infinity, then obviously log is monotonically increased, so S also goes to infinity, or the other way around. If S goes to negative infinity, then our price will approach L times exponential negative R over tau. Again, you kind of just want to start with the expression here. You just use the same logic as the ending part of topic 5. Yeah. It's just like use what you know to something you don't know. I don't know why I wrote T here, sorry. Probably talk for too long. So this is just S. And S goes to negative infinity. Right. So I guess nothing too complicated here. It's basically just you still want to look at S and T, but you kind of look at R as an expression of S and T as an expression of tau. For some reason, I forgot to paste the question for part 5 here. I'm just going to write down the question, sorry. Yeah. So part 5 is, part 4 is really just copying lecture slide and kind of just let us repeat what we know from the lecture. So I'm going to add a page here. I'm just going to write down the question. Sorry guys, I don't know why I didn't copy. So we consider a domain. So the question is, we consider a domain of S that is in S minimum and S maximum. We basically just consider a domain that is within T and T. And tau, sorry, not T and T, 0 and S. And we want to consider tau that is between 0 and T. And we set up a grid. Exactly as how I set up my grid a bit earlier, of Sn and tau of j, which is equal to S minimum plus n times delta S, and then j times delta tau. and n is equal to 0 until m plus 1, and j is equal to 0 until k. And again, even if they don't give you delta x, we should always know how to do delta x by ourselves, right? But this question is nice. They give us delta s and delta tau. And part A just asks us to use central difference approximation. Of big O delta S square. Again, central approximation always have big O of delta S square, right? This doesn't really change. To find dv ds and d square v ds square. So for part A, we just first calculate the first order derivative and the second order of df dt, and we sub in f for v and t for s. So we get this. Again, it's just applying the formula in the lecture. So part B just asks us to use forward equation. Sorry for just letting you guys watch me write here. But again, kind of just what we have on the lecture slide. And I think part C asks us to write down, I think part C kind of asks us to show that Vn of j plus 1 is equal to alpha times Vn minus 1j plus beta Vnj plus gamma of Vn plus 1j. Which is exactly the same as the lecture slide, but you just want to know how to find this yourself, right? So I will refer you to the lecture slide. I think I also wrote something here. Oh yeah, so we can just use part B from the previous part and substitute what I have in part A, right? Because I already have my dv ds and d square v ds square. And after some numerical manipulation, you will get the solution. I guess you just want to make sure you have enough time in the final to actually do this, because it is quite long. And I think part D is the initial condition. So this is the initial condition. And these two are the boundary condition. Again, it's just a continuation from the previous part. That's everything. I guess the bottom line is understand how we get the explicit implicit solution for the finite difference method. Understand Black-Scholes, understand put and call pricing, and make sure you leave enough time for questions 3 and 4 because it will be quite long. Yeah, sorry, my expressions in this workshop is a bit something. I guess I hope people found it helpful. And good luck for your exam.